Everyone to start 1220 elements of statistics. So today we are on chapter 3, that is basic concepts of probability. So we will start with 3.1, sample space, events, and their probabilities. So we are going to define these terms as we move on in section 3.1. Okay, so before we move on, there are some definitions here which need deeper explanation. So, first of all, we have random experiment. So, when we talk about random experiment, this is an experiment that you perform whereby you don't know the possible outcomes that actually come from this experiment. In view of that, you call that experiment a random experiment. Okay, so since you don't know the possible outcomes, you can't actually determine the exact outcome that actually came. In view of that, if you're able to collect all these possible outcomes that actually come from this random experiment, we call them the sample space of that random experiment. Okay, sometimes we would like to work with a subset of that sample space. If that happens, we call that what? An event. So an event is a subset or sub collection of the sample space. Okay, if this happens, then you might want to put a probability measure on the outcomes in the sample space. And this probability measure measures the likelihood that this outcome will actually occur. And this measure actually takes the range of 0 to 1. When the probability measure on a certain outcome is 0, then it implies that that outcome is impossible to occur. But when the probability measure on a certain outcome is 1, then we are certain that that outcome will actually what? Okay. So this is a brief thing about sample space, events, and their probabilities. So let's head to some examples. So you could have the sample space in our rectangle, and we have the event in the oval. So always the event is a subset of the sample space. So this actually is a diagram to explain the definitions that we have actually given. Okay, all right. There are some properties of the probability measure. We are saying that the probability of an event lies within the ranges of 0 to 1. It is neither less than 0 or greater than 1. It should be within what? 0 and 1, and 0 inclusive and 1 inclusive. And the second property is that if you sum all these probabilities, you should get what? 1. If you sum all these probabilities, you should get 1. Okay, so this is what we have now. So let's get to solve some examples. So now we've performed a random experiment by rolling a six-sided fair die. And if you do this, there are possible outcomes that come from this random experiment. And they are 1, 2, 3, 4, and 5. We put them into a set and we call it what? The sample space. So we use S to denote what? The sample space. And we call out an event. And the event is event A, which contains all even numbers. So you realize that event is a subset of that sample space. Then the sample space came out from what? A random experiment that we actually performed by rolling what? A six-sided fair die. Okay, so the event is for A, we will have 2, 4, and 6. And we are saying that another event B, which is the odd numbers in the sample space, and we are having it to be 1, 3, and 5. But with these odd numbers, we want the ones greater than what? 3. So 5 will be the odd number to be included in the event what? B. So we have a Venn diagram to represent what we are actually talking about. So we have the sample space to be this, that's the rectangle. We said we have A, which contains what? 2, 4, 6, and we have B, which is just 5. In all, if you union all these elements together, you should get what? Your S, which is what? The sample what? Space. And all of these elements should be within S. Okay, so whenever you are told to represent some kind of random experiments in a Venn diagram, you should know the event, you should know the sample space, and put the sample space in a rectangle, other events in what? In an oval, and list their elements in it, just as we've done here. Okay, so that is that. Now you have to put a probability measure on the outcomes in the sample space. So you want to ask what is the probability of rolling a 1, a 2, a 6. But note that each outcome in the sample space is equally likely to what? To occur. So we are saying that in view of that, then the probability of 1 is 1 over 6, 2 is what? 1 over 6, 3 is 1 over 6, true to 6, which is the probability of 6 is 1 over 6. If you want to simplify all these, then you're saying that the probability of I is equal to 1 over 6, whereby I is 1, 2, 3, 4, 5, and 6. Okay, so for each I, we are having this. For each I, I equal to 1, then it implies that it gets probability of what? 1 over 6. So if you simplify the whole of this could be written as that. Okay, that is what we mean. Okay, then we have to find the probability of A. Note that the probability of A is the number of good outcomes in A all over the what? The total number of what outcomes that we had in S. So we have 3 outcomes in A, so that would be 3 over 6. Or the probability of A is also equal to the probability of what? 2 plus the probability of 4 plus the probability of what? 6. Since each outcome is equally likely to occur, the probability of 2 is 1 over 6 plus what? Probability of 4, which is 1 over 6, probability of 6 is also 1 over 6. If you add all these probabilities together, you're going to get 3 over 6. And that reduces to 1 over 2. And in decimal, we get what? 0.5. So there's a 50% chance that the event A what occurs. Okay. So that is the whole concept of this probability. And you have to find the probability of what? Event B. But we've already found it here. So event B is equal to the element 5. So you have that answer here. You already have that answer here. All right. Okay. So let's move ahead. Now, suppose you flip a fair coin twice. So now we have a coin, and the coin has a head and a tail. If you flip a coin, you've performed some kind of random experiment, and the sample space involved in this random experiment is what? Head and tail. But in this case, you flip it what? Twice. So if you flip it once, there are possible outcomes of getting what? A head and a tail. So we use something we call a tree diagram to help us call out the possible outcomes from our random experiment. So if you flip it once, we get what? The head or what? Or a tail. And we need to flip it twice to get to know all the possible outcomes that can come. So in case we get a head in our first toss, then the second toss we could get what? Head, or we could get what? A tail. Or in case in our first toss we had a tail, then we could get what? A head or what? A tail. So if you match all these possible outcomes together, so if our first toss gave us a head, and the second toss also gave us a head, then we could have what? Head, which is here. Or we could have what? Head, what? Tail. Or we could have tail, what? Head. Or we could have what? Tail, what? Tail. Okay, so whenever you want to find the possible outcomes from a random experiment, you can use what? The tree diagram to do that. But note, always there is some ways in actually getting to know the possible outcomes that will be within what? The sample space. We are saying that if you toss a coin once, then it implies that there are 2 outcomes involved. But if you toss it twice, then we have to multiply 2 by 2 to what? To get 4. And if you toss it 3 times, you have to multiply 2 times 2 times 2, then we get what? 8. And if you toss it 4 times, then you have to multiply these 2 possible outcomes 4 times to get what? To get 16. Okay. All right, so these are the total possible outcomes. So sometimes you might not need to actually list the possible outcomes, but what is the total possible outcomes in the sample space? That is what is very important. Now we toss a coin. We know that there are 2 possible outcomes, and we roll a die. So there are 6 possible outcomes. You can match these. So in the total number of possible outcomes is what? Is 12. Okay, so 2 by 6, you get what? 12. You can use a tree diagram to represent that, and you will get the total number of possible outcomes that you're going to have. Right, so this is as simple as that. Okay, so we have to use a tree diagram to solve this example. Right, but note that the possible outcomes are left and right, and we have 3 vehicles. Okay, each at the end of a ramp turns left or right. Okay, so the first vehicle turns left or right. So if you are the left, then the second vehicle could also turn left or right. So we do this for all these vehicles, and at the end, we will be having the total possible outcomes to what? To 8. To the 8. Okay, so if you want to know the sample space for this kind of experiment, then we can actually match them. So if you are the first, we have what? The left, the left, the left. Or we could have the left, and the right. Okay, so this will help us list the possible outcomes that you have here. In case you have to use a tree diagram to list the possible outcomes of this example that we are having here. Okay. Okay, so we are done with 3.1, and we talk about that is the sample space, the events, and their probabilities. And note that the probability of an outcome always lies within the range of 0 to 1. It is not below 0, that it implies that we can't get negative probability, and it is not above 1. It is within what? 0 and 1, and 0 inclusive and 1 inclusive. Okay, now we are moving on to 3.2, that is complements, intersection, and union. Complements, intersection, and union. What do we mean by complement? So when you talk about complement of an event, then we mean that the elements in the sample space for which you can see in the event that we are talking about. So if A is an event in the sample space, then what are the elements in the sample space for which you can see in A? Then we have something we call what the complement of what A. So we denote it by this symbol. Okay, that is A with a superscript of what C. This implies that A complements. Okay, so there is a probability rule for complement. The probability rule is that probability of A complement equal to 1 minus what the probability of A. We might employ this in the following examples, or in case of anything that you see you want to apply this, it will be very useful for you to apply. Okay, and also we can actually resolve this to get the probability of A plus probability of A complement to be equal to 1. Since we have probability of A complement equal to 1 minus probability of A, then we are saying that we can add plus what? Probability of A here, and we can add plus probability of what? A here. So this will cancel this, and it implies that we're going to have probability of A complement plus probability of what? A, then equal to 1. Okay, so this is another way of representing it. Okay, so let's get to solve some examples. So now we have a six-sided fair die, and it is rolled. Okay, so we know the possible outcomes that come from this. That is, we have the S to be what? 1 through to 6, and we define an event A contains all even numbers, so we have it here, and we have event B which contains all odd numbers greater than 3, so we have it to be here. Okay, so we want to list what is A complement. That is what the question is asking. What is A complement? And what is the probability of A complement? Okay, so A complement, they are the elements in the sample space for which you can find in A. So what is A complement? So we have the A complement to be 1, 3, and what? 5. And probability of A complement. So what are the number of elements in A complement over what? The total number of outcomes you have in the sample space. So we have 3 outcomes. That is 1, 3, and 5. And so you have 3 over 6, which reduces to what? 1 over 2. So there's a 50% chance of this occurring. Now, we move on to what is B complement. So what are the elements in a sample space for which you can't find it in B? So we have 1, 2, 3, 4, and what? 6. 1, 2, 3, 4, and 6. So these are the possible outcomes in the B complement. Okay, so there are 5 elements in B complement. So 5 over 6 gives you the probability of B complement. Okay, all right. So that's what we have here. Now, a fair coin. Now we are tossing a coin. Okay, fair coin is tossed twice, so notice that we have 2 times 2. It gives us 4 total possible outcomes. Okay, so what is A complement? We define A to be the event that tails is not flipped. So event that tails is not flipped. So the possible outcomes that you could have is what? We have head, 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 tail, tail, head, and tail, tail. So if tails is not flipped, then we only get what? Head. You only get what? Head for A. You only get head for A. Okay, so that is what you have here. Okay, so you can use the tree diagram to also write out what the possible outcome that comes from it. So A complement will be the elements in the sample space for which you can find it in A. Okay, so what are the elements in the sample space for which you can find it in what? In A. So we have it what? Head, tail, tail, head, and what? Tail, tail. So that is what our A complement. Then we want to find what is the probability of A. What is the probability of A? So here we have probability of A. Then A only has one element. That should be 1 over what? 4. That should be 1 over 4. 1 over 4. Okay, so that's 25% chance that A occurs. And what is the probability of what? A complement. What is the probability of A complement? So for here, we know the number of elements in A complement, which is what? 3. So which is 3. So you count the number of elements over the total number of elements in the sample space, which is 3 over 4. It gives you that. Or you could use the probability rule for complement. That is probability of A complement equal to 1 minus probability of what? A. So we know A to be probability of A to be 1 over 4. So this will be 1 over 4. 1 minus 1 over 4. And you are going to get 3 over 4. Okay, so in case you want to use the probability rule, then this also works. Okay, now you toss a coin 5 times in a row. What is the probability that you flip? You flip at least one head. You flip at least one head. So you toss coin 5 times in a row. So what are the possible outcomes that we get from this? So you're going to multiply 2 times 2 times 2 5 times, then we get 32 possible outcomes. So at least one head means that if you want to work this in a smartest way, then you can take the complement of it, then you can know what the at least. So if your A, in case your A, coming, in case your A equal to at least 1, at least one head, then your A complement would be no head. No head. Then this implies that within this, there is only one element which has no head, and that should be what? Tail, 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 tail. So A complement will have only tail, 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 tail. And since we know that there are 32 outcomes, then in case you are asked about the probability of at least one head, then it should be probability of A to be equal to 1 minus probability of what? A complement. And we know probability of A complement to be 1 minus 1 over what? 32. And this gives you 31 over 32. So this will help you work it out. Okay, and there's a way to also get at least one head. Okay, so at least one head means that we are going to have head, tail, 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 head, 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 and this is a lot of work to do. That is why the probability rule of complement works a lot, which simplifies some certain situations. Okay, so you're having probability of at least one head to be 31 over 32, or you can work it in this format. All right. So now we've been given a table for us to actually find certain probability. Okay, we know that when you sum all the probabilities together, so we have a table here. We have the male, we have the female, and we have some probabilities of some candidates A, B, C, D, and E, where D and E are female candidates and A, B, C are male candidates. Each of them has their probabilities. Each of them has probabilities, but there was left probability here for E. So we are told to find the probability of E. But note that when you sum all these probabilities, you should get 1. So what number should be added to the numbers that we have so that we get to 1? Okay, so that is the whole concept. Then they're saying that add the numbers that you know and subtract from one, then you get the probability of E. So that is what we did. That is what we did. So we had it to be what? 0.30. So we place it back here. All right. That is the whole concept. So what is the probability that a female candidate will be voted into the office? So what are the female candidates that we're having? Is D and what? E. So female equal to D and E. So probability of female equal to probability of D plus probability of what? F. So that gives us what? 0.50. 0.50. Okay. Now we are on intersection. Intersection means that we want to find the elements that is in one event as well as in another event simultaneously at the same time. Okay, so we want to find some common elements you can find between two events or three events or more. That is the use of what? The intersection. Okay, so that is the whole concept. So we have a diagram here that actually explains what the intersection is. So we have the diagram here which explains so. Okay, let's move ahead to get to know some examples. And okay, there is another definition here. We have something we call the disjoint or mutually exclusive. This also uses the idea of what? Intersection. But here we mean that if you intersect two or more events together and there is no common element, then it implies that they are disjoint. We can't find any common element in it. So this one, let me stress much on it. So we are saying that if A, I'm coming. If A in hi, I'm coming. Okay, if A intersection B, if A and B are two events, and we get their intersection to be a null set, or something. So these two symbols represent what? An empty set or what? A null set. If you don't have any elements common between A and B, then you're saying that A and B are what? Disjoint. I think this definition works best for me than finding the probability of A intersection B to be what? 0. Okay. So if you find any two events and they are common element you can't find such, then we are saying that those two events works are what? Mutually what? Disjoint. Mutually disjoint or mutually exclusive. So you can use this as well. Okay, in case probability of intersection B equal to 0 is something confusing, then use this to denote that. If you can't find any common element, it means that you can use just two curly brackets with no element in it, or you can write something and cancel it. So that is what we have for the second one. We call it the phi. Okay. Or this definition, if that also works for you, then you are good to go. Okay, but I prefer this. This is very simple to go with. So you have to consider the following sample space, and you have event A and B and the probabilities of the 10 outcomes in S. So you have event A to be 1, 2, 8, 9, B to be 2, 3, 5, 6, and C to be 3, 4, and 5. So we have the probabilities of each of these 10 outcomes, but you are left with 5. But note that the sum of all these probabilities to be what? Should be 1. So since we know we know 9 of them, then find a probability of 5 is easy. Add all the events and subtract from 1, you get a probability of 5. So you're going to get a probability of 5. Okay, so that's what we did. So now you have to draw a Venn diagram. This implies that S will be the rectangle and you're going to have ovals in it. Okay, so you draw 3 ovals so that you have event A, B, and C. And these 3 ovals, label them. Call them A, B, and what? C. And the elements in A, you list it, and the elements in B, you list them, and the elements in C too, you list them. But note that some of the elements that appear in one set might be in another set. So, but the S should contain all the 10 elements that you are seeing. So A has 1, 2, 8, and 9. So you could see 8 here. You could see A here. And B also has 2, 3. So you have 2, 3, 5, and 6. Okay, so that is this means the elements in B, and this also means the elements in what C, but there is some kind of intersection. That is why we have 3 and you have 3 and 5 in B as well as what in C. So only elements that is in C is what is 4, which you can find in B as well. Okay, so this is a way to represent it. There is different ways in drawing it to represent it. Okay, all right. Then we ask ourselves, what is the probability of the outcome 5? So that is just what we did. We added all what the probabilities that we know, subtracted from 1, then we had it to what? 0.12, 0.12. So that is the probability of 5. Probability of 5. What is the probability of event A? So we have A to be 1, 2, 8, 9. So, but we have each of these events. So probability of A is probability of 1 plus probability of 2 plus probability of 8 plus probability of 9. Okay, so you have it to be 0.1, 0.08, 0.07 plus 0.22. So we had the probability of A to be what? 4.47. So this means that the events are not equally likely to occur. They are not equally likely. This implies that we can have 1 over 10, 1 over 10 for each of them. Their probabilities what varies. So that was why the probabilities were given beforehand. So it implies that probability of A means that add the probabilities of each of the elements in A together, then you are good to go. And what is probability of B? It's also like just as you did for A, do same for what B, then we get what this probability. Then we want to find what is the probability of A intersection B. So we find the intersection between A and B. So first of all, before you solve this, make sure you have A. What is A intersection B? What element can you find in A as well as what in B? So let me clean this part so that you see it well. So you realize that there is 2 here. So 2 is the element you can find in A as well as what in B. So we have it to what 2. Right? So there exists an intersection here. It implies that A and B are not mutually disjoint or mutually exclusive since you find an element in their set. Okay. So what is the probability of this? So the probability of A intersection B is the same as probability of 2. Okay. So we have it to be 0.08. 0.08. Okay. Then what is the probability of A complement? Since we know the probability of A, we can use the complement rule to do it. So probability of A complement will be the probability of A complement equals 1 minus probability of A. We had A to be at 0.47. So this is one of the uses of the complement rule for probability. Okay. So we have it to be 1 minus 0.47. Then we have it to be 0.53. What is the probability of A intersection C? Okay. So what elements are in A as well as in C? If you go back to the diagram, you realize that you wouldn't see any element that is in A as well as in C. You just go, this is A, this is your A, and this is your C. There is no common element that you can find in A as well as in C. So this implies that A and C are what? Mutually what? Disjoint. A and C are mutually what? Disjoint or mutually exclusive. So their probability gives you what? 0. Their probability gives you 0. So that is what we've actually represented here. Okay. But you want to find probability of A intersection B intersection C. So here you want to find an element. You can find in A as well as B as well as C. There's such no element. Or you can find an element in A and B. You can find an element in B and C, but you cannot find an element that exists in all 3 of them. So if that happens, then there exists none. So you use the empty set to represent it. Use the empty set to represent it. And if that happens, you're saying that the probability is what? 0. The probability is 0. The probability is 0. Okay. If you also use a Venn diagram to represent it, so always this is the common what intersection of the 3. Okay, there is no common intersection between the three. Can do such, you wouldn't find. Okay, so now we're on the union. We are on the union. We are actually getting close. Okay, definition, that's union. The union of events A and B, that is denoted as A union B. When we talk about union of two events, we imply that we want to add the elements of those two events or three events together. Okay, if you find an event repeating itself, just write it once. Just write it once. We want to add all those events into one what event. So that is the idea of the union. So we use this symbol to represent it. So this is the symbol used to represent it. Or in words, you can find or. So A or B. This implies that you use this symbol to represent it. You know the definition of it. It implies that add the three events together, their elements, add them together. And there's by this, if you want to assign a probability to such an event, we are saying that the probability of A union B or A or B is equal to probability of A plus probability of B minus the probability of A intersection B. The reason why we have to minus one is that if you pick A, it contains the intersection. If you pick B, it contains the intersection. So here we have the intersection twice. So we have to subtract one from it so that we can find the probability of A union B. A union B. Okay. So this is the rule for it. This is the rule for it. You can apply it anytime. Okay, so here we are using examples that we had above. We have A, B, and C. So we want to apply the examples that are here. You mean the examples that we see here. The examples that we see here, that is what you're going to use to solve the unions. Okay, so let's move ahead. So if you have to find probability of A union B. So by the additive rule, we are having probability of A plus probability of B minus the intersection. So we have it to be probability of A, we have this, B, we have this, and the intersection too, we have this. So, we have the union, probability of their union to be 0.69. We apply the same idea to A union C. And here, since there was no intersection between A and C, so we have it to what? 0. Then we have our final answer to be 0.76. 0.76. Okay. The following table gives the breakdown of 1,000 residents of a particular local according to age and tobacco usage. So we have smoker, we have non-smoker, we have under 30, we have over 30, and we have a two by two contingency table. So this 2 by 2 contingency table records the number of maybe smokers and or tobacco usage and age. Okay, so it records the number. But in this age, we have two levels. We have under 30 and over 30, and the tobacco users too. We have the smokers, and the non-smokers. So the in between records the number or the intersection between these two levels that you're having. So the 50 here means that we have 50 smokers who are under 30, and the 200 here means that we have 200 non-smokers who are under 30. So for under 30 own, the number of people who are under 30, we have 50 plus 200, that gives us 250. The same applies to over 30, we have 200, we have 550. If you add them together, we have 750. Always the numbers at the column, the total number at the column, and the row always match to this. What we have here, that is 1,000. So the total number of those that smokes are 250. That is 50 plus 200. Non-smokers are 750. That is 200 plus 550. Okay. So we have to use this contingency table to answer the questions that actually follows. So one of these residents is selected at random. It implies that each resident is equally likely to be selected. We are not being biased. So you are saying that you have to find the probability of each of the following events. Find the probability of each of the following events. So the person is a smoker. So the person is a smoker. It implies that you have to find the total number of those that smokes over the total number of residents that you have. And but it doesn't end there. So the person is a smoker who is what under 30. So there exists an intersection. So this is the person, these are the people who smokes. But we also let me clean this part so that you could get a clear picture of what I'm drawing. Okay. So this means that we have 250 people who smokes. And those under 30, these are those under 30. So there is this an intersection here, which is what the 50. So this implies that you have to find a probability of smoker intersection less than what 30 or under what 30. And that gives us 50 over the total. So always what we are saying should be over what the total. What we are talking about should be over the total to give you the probability of interest. Now we are finding the person is a smoker. So this one we are only interested in those that smokes. So how many people smokes? So realize that you have 250 people that smoke. So in this column, sorry. So you have 250 people who smoke. So that is 250 over the total. Okay. That is how we work it. The person is over 30. So we go to the 30 row. So 30 over 30. So we have 750. 750 over the total. And the person is over 50 or is a smoker. So we are using or here, means a union. So probability of over 30 union smoker, and we have the additive rule to be what? This plus this minus what their intersection. So we have over 30 to be what? 750. We have smoker to be what? 250 over 1,000. And their intersection is what? 200. So we have it to be here. So we have it to be this. That's 200. 200. Okay. Then we apply the additive rule and we have our final answer to be 0.80. 0.80. Okay, interesting. So this actually talks about the 3.2, that is the complement, intersection, and what? Union. So we've discussed 3.1, the sample space, events, and their probabilities, and we've talked about intersections, complement, and what? Their unions, and how to assign probabilities to each of them. We have the probability for complements, and we have the additive rule as well. In each case, you can actually apply them and to get your probabilities. Okay, so now we are going to the conditional probability and independent event. Okay, but I'll take this the next day. So we'll end here for today, and I'll continue for tomorrow for this. Okay, thank you all. See you later.